Alright guys, so here's what I want you to do. I want you to look at this, por favor. Now, here's the first thing that we've got a reaction. We'll write this in just a second, but I want to focus on the video for just a minute. So write the balanced equation for the reaction of lead to nitrate with sodium iodide to form sodium nitrate and lead to iodide. Just reading the words, can you tell what type of reaction this is? It's double replacement. Okay, so but here's the problem. Matter of fact, let me go to this real quick. Let me go to this because I want to highlight a few things. Don't write on this sheet yet. We're going to come back to it in just a minute. So if I start with, so notice how they've already phrased this question. If I start with 25 grams of lead to nitrate. Now let's go back up to the top. It says, write the balanced equation for the reaction of lead to nitrate. So how much do they give you of that specifically? 25 grams, okay? So they tell you, boom, I've got 25 grams of that. And this is where it gets a little different from what we've done in the past. And is the key word there, and 15 grams of sodium iodide. So when we go back up to the top, it says, write the balanced reaction for the reaction of lead to nitrate with sodium iodide. How much sodium iodide do you have? 15 grams. And then here's the question. The question is, how many grams of sodium nitrate can be formed? How is this different from what we've done in the past? There's two pieces of data. Well, the problem is, do you agree that both of those pieces of data in green and blue are reactants? Okay, and we're trying to go to what? A sodium nitrate, which is a product. Well, that is a problem because which number set do I pick? Do I pick the 25 grams of lead to nitrate, or do I pick the 15 grams of sodium iodide? Hold on before you answer that. Here's the answer I get every single year. I always get 15 grams of sodium iodide because it's less. Plausible. I can see your thought process of why that makes sense. Well, you have less grams of sodium iodide, so that's gonna you don't have enough of it to go around. Understandable, but here's the problem with that. Up until this point, we've talked about how do you compare two different compounds. How do you compare them? Mole to mole. What is the problem with the data that they have given us? They're in grams. So, here's the deal. If I tell you that we have 50 hamburger patties, and I tell you that we have 60 pounds of hamburger meat, and each burger is a pound, how many burgers can we make? Why 50? Because I only have 50 buns. Well, that's going to be something that's going to make our reaction stop. We're going to be able to stop cooking. Well, the problem is, what happens if we're baking cookies? Does every single part of a cookie recipe call for the exact same quantity of things? Well, if I've got a dozen eggs, I've got a pound of flour, and I've got 10 ounces of oil, well, it depends on how they mathematically relate to each other. So the problem is we can't compare grams. Okay? So I want you to go up here to the top, and I want you to make two little notes. The first thing I want you to make, actually three little notes. Put a little X through the word reagent and write the letters RXT. Now, what do RXT stand for? Reactant. Now, you should know from this point that reactant is what RXT is. So I'm not going to call it limiting reagent, but if you see reagent, just flip it to reactant, okay? So that's step number one. Number two, out beside this, and make it so you know that you're talking about the limiting reactant. The limiting reactant runs out first. It runs out first. So for baking cookies, that's what's going to stop me from being able to continue to make more and more and more and more cookies, okay? So the limiting reactant runs out first. The second thing I want you to write is, and this is the most important, you can't compare grams. That is problem number one with this problem they've given us. You cannot take two compounds that are different and compare them using grams. So what we're going to do is sometimes it's easier if you see a video and hear someone explain it and let me kind of talk you through it while we're working on something. So let's watch this little quick video and let's see what this guy is talking about and how he kind of portrays it. I did. Thank you. Can't compare grams. Thank you. Balancing chemical equations. Blah, 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 blah. Aren't you glad I'm not like that? Which are the good stuff? Congratulations. All right, so here's the point. If we were going to make some biscuits, his recipe says we need 4 cups of flour. What is TSP? Teaspoon. Okay, teaspoon. 1.5 cups of milk. What is TBSP? Tablespoon. And then a 1/3 cup of shortening. That's a funny word. That's an old-timey thing he's using right there, okay? And if he has this much, what's a good word? Stuff, yes. That much stuff, how many biscuits can he make? 24. So we're just cooking biscuits right here. But if you have any less of any of that, can you make 24 biscuits? No, and that's the problem. So as of right now, do you agree that this is a perfect recipe to make a perfect quantity? In chemistry, if we're trying to make a perfect reaction, we want to make sure that we have a perfect quantity. So because is there any reason to buy a whole lot of extra if we just want to make a certain amount? If I need 24 biscuits, there's no reason for me to go buy 8 pounds of flour if I only need 4 cups. Okay, so we know exactly how this recipe works. So this is kind of, I want you to think of in chemistry in terms of if I have a certain amount of reactants, I can make a certain amount of product. But I want to try to limit the amount of excess that I have because that's just a waste of money. That's just a waste of my resources. All right, so let's ponder that. So we're going to change our 4 cups of flour to 2 cups. Is that going to yield what my recipe calls for? No, that's going to make my recipe be more or less than what it yields. Less. How much less? Half. Very good. If I've half my cups of flour, and I have to half my biscuits. So this is what we're talking about in terms of limiting reactants or excess reactants. Because what have I just limited? The amount of cups of flour. So, but the problem is, it told you exactly what your limiting reactant was. Sometimes you may not know. What if I gave you these ingredients and I said, figure out how many biscuits I can make? Well, then you have to figure out exactly what the chemistry was between these things. And that's where our goal is. I'm going to give you a certain amount and say, how much can you produce? Well, you don't know which one is going to be limiting. We're telling you in this case. Yes. So now do you hear why I said it runs out first? So basically that is what's going to limit your reaction and make it stop. You can't continue if you've ran out. I'm sorry. All right, I want to ponder this one just real quick. So, if I have 100 grams of nitrogen and 100 grams of hydrogen, how many grams of ammonia would be produced? My first question is, isn't this a special type of reaction I told you about? What is the name of this type? Hey, Rabash, we're good. Very good. So, but here's the deal. I'm starting with the exact same amounts. So, logically tells us, all right, 100 grams, well, that means I can make 100 grams of product. Well, or I can make 200 grams of product. But what's the problem with what they've given us? You can't compare grams. That's the issue, is we've got to figure out how to compare these things. Because nitrogen and hydrogen, are they the same or completely different? Completely different. The size, the shape, the mass, all these things are totally different. So we've got to figure out which one of these is going to limit our reaction. So this is what we're going to get into. And this is what I've told you. Remember, a must is a balanced equation. I show y'all videos like this so you appreciate me a little bit more. I do. That's why I show you this. I really do show you this. All right, so do you agree that that's the balanced equation? So what they've done is they've given us 100 grams of both of these, and they ask us specifically, how much product can we make? We can count. All right, we gotta go. We gotta move a little faster. All right, so here's the first thing. Yeah, he messed up. So here's the first thing. I've always told you that you can't compare what first? You can't compare grams. So what's the first thing he did? He changed it to moles. Now that's the key. So, matter of fact, I hate to do this. Go away, trash can. Right here, by number 2, keep it as far left as you can keep it. Write steps and underline it and write the number 1. Okay? Step number 1, convert grams to moles. Now, what if we read a problem, they've already given us moles? What's the great news? You can skip the first step. That's the great point. Okay? Does that step remind anyone of something we've done before? What's that thing we use this for? Yeah, what do we use it for? Empirical molecular formula, right? Okay? All right, so that's our first step. And so now we've got this concept of we can compare moles. Which one of these is the least amount? Nitrogen. Now, we can't determine yet exactly if this is the limiting reactant because there's one more step we got to go through. But as of right now, it's pretty obvious that nitrogen has the potential to be our limiting reactant. You got really excited all of a sudden. All right, so this is the next step. So step number 2. What did he just do? It is a he. Say that again. Mole to mole ratio. Hang on. Don't write anything yet. Okay. So this is what you want to do. You want to and this, you can write it like this: mole of reactant. Step 2. Mole of reactants with an S. 2 moles of. Hang on. You answer this for me. Not product. Basically, what they're asking you about. I don't want to say the word question. It's the compound they're asking you to find, and I don't want a word for that. The unknown. Perfect. Well done. The unknown. So we're going from the moles of the reactant to the moles of the unknown. Well done. Good job. Now, in this question, the question was, how much ammonia can be produced? Well, ammonia is our unknown. And so this is what we've done. Okay, everybody cool with that? So, final step, and this is the easiest step. Step 3, the least is the LR. Now, what in the world does LR stand for? Limiting reactant. So now that we've converted our moles of reactant to our moles of unknown, the least number is our LR. But here's the problem. The least number tells us our limiting reactant. Is ammonia even a reactant? No. What is the reactant that's limiting us? Nitrogen. So you see the difference there. So just because we have the least number as ammonia, we've got to say, okay, well, where did this come from? It came from which part? The nitrogen. So if we go back and we look at the very beginning of this problem, we started out with the exact same amount of hydrogen and nitrogen, right? But because one of them is less product, what is the most we can make? The most or the least? The most we can make is the least that is produced. Think about that. The most we can make is the least that is produced. The most we can make is the least that is produced. Yes. Yeah, the least is the LR. Exactly. Because it's the least that's produced. It's already started. All right, so again, that's where he's going, and then he converts it grams to moles. All right, so let's actually work our own problem. I wanted you to see it visually before I worked it. Okay? All right. That's all. So here's the first thing let's do. You have a balanced reaction you have to write. So lead 2 nitrate. What's lead 2 stand for? Pb2 plus. Nitrate is NO3 minus. So Pb NO3 2 plus sodium iodide. What group is sodium in? Na plus. What group is ion? 17. So NaI reacts to form. Now, if I just stop right there, could you predict the products off this? What type of reaction? Go replace them, just swap them all over, right? So I've got PbI2 plus NaNO3. This is the same thing we've always done. Oh, yeah, the word says sodium nitrate first, sorry. I just did it out of my habitual, what's first on the left is first on the right. All right, is it balanced? How do you balance it? I need a 2 there and then a 2 over here, right? All right, so 1, 2, 1, 2. So that's going to be our balanced equation. Now, so here's the deal, and I'm going to have to kind of scrunch this in, but we already know what the problem with this is, and I've already told you about it, right? Have you been given 2 given amounts? And we've got 1 unknown. So the problem is, and I'm actually going to work on a different page so I can so we can bounce back and forth with this. So let's write down what they've given us. So they've given us exactly 25.0 grams of what? Is it lead 2 nitrate? Okay. All right. So PbNO3 2, and they've given us 15.0 grams of. Why do I keep doing parentheses? Of NaI, right? All right, so I'll promise I'll come right back to this. So steps, and I'm writing this just for everyone at home. First step is convert grams to moles. The second step is we're going to go moles. What did y'all write? Moles of what? Moles of reactant to moles of unknown. And then the last step's the easy step. The least value equals the LR. Everybody okay with that? Guys, this is the first year I've taught it this way, and I saw something in this video that made this way look a little bit better to me. So you're going to get the good version. All right, so let's go back and let's look. So what's the step number 1 that you all should know how to do? Convert grams to moles. Okay, so we're going to go from grams of PbNO3 to moles of PbNO. Yes, thank you. PbNO3 2. Okay, same thing on the bottom or on the other one. Grams of NaI and grams. Excuse me, not grams. We're going to moles. Moles of NaI. Has anybody seen my big blue calculator? It has gone missing. Peyton took it. That's exactly who did it. I'm just kidding. Right, do you have the masses for these? Okay. That's why I need money. And I've got that. I know lead is 207.2. Yeah. Stop it. All right, so there's our masses right there. So lead 2 nitrate is 331.24, and sodium iodide is 149.89. God bless you. All right. So then we just divide how we always do. 25 divided by 331.24 is equal to 0.0755 moles of PbNO3 and the bottom one is 15 divided by 149.89, and that's going to give us 0.100 moles of NaI. Yes, ma'am. For me? No. I mean, we only have like 20 minutes left. Yeah. Okay. All right. So far everything smooth, right? This is step 1. Now I'm going to have to go to the next page, but you guys can keep working it on out. What's step 2? Convert moles of the reactant to moles of the unknown. So we had 0.0755 moles of PbNO3 and then we have 0.100, God bless you, moles of NaI, and we're going to moles of the unknown. I hate writing polyatomic compounds. What's the compound they're asking us to go to in the question? Sodium nitrate. So NaNO3. Alright, so have we done this before? What step is this? This is your mole-to-mole step. Where do these numbers come from? The coefficients. I'm going to go back and look. Sorry, that's the wrong button. So the mole-to-mole ratio of lead 2 nitrate to sodium nitrate is a 2 to 1. And what is it from sodium iodide to sodium nitrate? 2 to 2. So when we come here, we're going to have a 1 over a 2, and here we're going to have a 2 over a 2. All I did was just plug in the coefficients. Flip the top one. Oh, it is. Thank you. Sorry, I messed that up. That's why sometimes I hate working on this with stoichiometry, because I don't get to see them. Alright, so this is 2 over 1. My apologies. I don't see the balanced equation. Sometimes I forget what the number is. Now, we've got to do a little bit of math. Do I have to do anything to the bottom one? Why? 2 over 2 cancels, which gives me, obviously, again, 0.100 moles of NH3. And then the top one, 0.0755 times 2. The last problem. The video problem. I did that yesterday. Wow. At least I'm consistently bad. Being consistently bad? No. 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 I did it again. All right. So here's the deal. So what we've just done is nothing different than we've always done. The only difference is instead of doing it once, we've done it twice. Same thing. I know what you're asking. Why do I have to do this twice? Why am I having to do limiting reactants? Whenever you have to do this in terms of a laboratory experiment, or even if you're at home cooking, or you're not going to go run out and buy a bunch of random crap to just hopefully throw it together and make it make sense. Okay? Some of you would, but if you are a professional chef, you have to make sure that you meet certain quotas and meet certain stocks. Are you going to be able to do this in terms of chemistry? No, but you can apply this stuff to real life. So here's the deal. What is step number 3? The least is the limiting reactant, but here's the problem. The limiting reactant is not what you're looking at over there, because what you're looking at over there is the what? That's the product. That's the unknown. So which value is the least, which gets me to my limiting reactant? This right here is my LR. Does that make sense? Because this number is smaller than this one. So when we go back to this, and again, I know y'all are working on this, this is the part that I want you to circle this and say that this is my LR. Okay, so look at question 3. What does question 3 on the sheet of paper say? What is the limiting reactant? What would you write? Not 2NaI, just NaI. But here's the problem. Have we actually answered the question yet? No. What was the question in the very beginning? How many grams, again, this is the key right here, how many grams of sodium nitrate can be formed? Well, what is the best news about the data that we have? Don't we already have moles of NaNO3? What do you have to do? Just convert it to grams. That's it. So what we've now done is we've actually kind of stepped ourselves through it. So we're going to take this, and we're just going to take it to grams, and we're done. Okay? So 0. What was it? No. What? No. This is still number 1. And here's the reason why. It's because, what's wrong? So my question to you is, we've done the work twice. The whole purpose of doing it twice was to find the limiting reactant. Now we've got to answer the question. We just determined it. No, y'all. We're still on number 1, guys. No, it's not. Listen. The question 1 says, if I start with 25 grams of lead-2 nitrate and 15 grams of sodium iodide, how many grams of sodium nitrate will be formed? Yeah, this is all one problem. Write it under number 2. You can keep writing it under number 3. This is not confusing. This is so not confusing. So if you look at this, number 3 it's a what is question. What is the limiting reactant described in problem 2? Sodium iodide. So that's the answer. But look at the question in number 2. How many grams of sodium nitrate can be formed from what we started with? So where we ended last was we had 0.100 moles of NH3. So this is where we ended. But from this, what can we do? God, I did it again. NH3 is a lot easier to write. So I've got moles. What do I do? Because the question is grams. Just convert it to grams. So moles of NaNO3 to grams of NaNO3. Thank you. What's the final answer to 3 sig figs? It's going to be 8.50. So in the end, the only difference between this and everything we've done before is in the beginning, instead of just working 1 gram to gram, or 1 mole to mole, or 1 mole to gram, you've got to do it for both reactants to find the least. That's why we have to do this. This is the easiest way I've ever taught it. I promise. You don't want to see the other ways. It's just one more step. Okay? Yes, sir. There's not a test tomorrow. Where did y'all come up with this idea there's a test tomorrow? Yeah, there's not a test tomorrow. That worksheet is due tomorrow. Yes, ma'am. I haven't even started. The reason why is because I've got the Honor Society stuff. I've time to do it all. Alright, so we're going to stop here for today. We'll talk about how much excess is left over tomorrow. Yes. Basically what you would do is you would go back. Here, let me stop the video.